Okay, so today we're going to talk about extending our one-dimensional problems to to multiple dimensions, like two-dimensional, three-dimensional problems, because very rarely do we actually use solve one-dimensional differential equations in our field. So we need to extend our methods to two or more commonly three dimensions. Conceptually, there is no real big deal in extending our finite difference approximation to say two or three dimensional problems. Just we can use direct extension. We just write our derivatives in say additional dimensions, same way as we wrote them for one-dimensional case. The problem though is twofold. First of all, some schemes that are stable for one dimensions may become unstable in two or three dimensions. That's kind of weird, but that's the case, and we'll consider one example of that. And also stability criterions that we developed for one-dimensional case can actually be different for a multidimensional case. In fact, usually the constraint on time step, for example, is actually stronger or more restrictive than in one-dimensional. And let's first consider this point. Just demonstrate that extension of our, say, upstream bias scheme to two dimensions will automatically reduce time step necessary for stability. So if we consider our advection, let me take this. So we have our advection scheme, advection equation in two dimensions this time, where u and v are transport velocities in directions x and y. If we use upstream bias scheme, we have scheme like Km. So we have now two indices equals to phi Km n minus. So we introduce our mu's, also non-dimensional current numbers, mx equals to u delta t divided by delta x, and mu y equals to v delta t divided by delta y. So then we can write our scheme as the following. So it's upstream biased. So this is upstream biased in x direction, and this one is upstream biased in y direction. So this is our direct extension of our one-dimensional upstream bias scheme to two dimensions. We just add additional term here. So it's kind of seems like straightforward. So if we now analyze stability, so we look at our solution in the form like before Fourier modes, but this time in the two directions. So then we will get the following equation. It's analog of our one-dimensional stability equation. So this is the equation we considered before, and now we have this additional term. And if we do the same kind of graphical analysis of this in complex plane, will actually conclude that stability criterion here is just basically the same, except that it looks like the following. That actually the sum of mu's should be smaller than 1. And before we had that only one mu smaller than 1. So you see that in this case it's a different stability criterion. And so let's so what it means when for example you have two-dimensional flow, so in x and y, and it's all like, let's say that it's all in, so your u's look like this. So all the flow along the x, of course, then there is no flow in y direction, then the scheme becomes basically effectively one-dimensional, and then you have stability criterion that your mu should be smaller than 1, mu x. So you see, the only difference appears here when you have diagonal flow like that. So if you have a flow like that, this is your c vector, velocity vector. Then we have both mu x and mu y, and of course the effect is maximum when it's like exactly 45 degrees, assuming that also we may assume that delta x and delta y is the same, which is usually the case if it's like a two-dimensional flow in the horizontal plane, let's say. So so here we have what this one is written as so mu x, so it's delta t divided by delta x, and we assume that delta x is delta y. And here we have u, which is, so we introduce c as a just wind, total wind magnitude. So it's square root of u square plus v square is equal to c. Then we have that u is c. So this is our angle here. So it's c cosine theta plus c sine theta. And this is smaller than 1. So now, of course, maximum, this cosine plus sine, so c can be taken out. So now it's current number based on the absolute velocity, on magnitude of wind. So cosine plus sine, actually this function, it has a maximum at theta equal 45 degrees. It's very easy to show, just differentiate it with respect to theta and equal to 0, and you'll see that the solution is 45 degrees. So so for 45 degrees we have now our condition is delta Tc divided by delta x, and here is cosine of 45 degrees equal to sine of 45 degrees. It's square root of 2 over 2, and 2 of them times 2. So it's equals to, and it should be smaller than 1. So 2 will cancel, and we have our condition that delta t times c divided by delta x smaller than 1 divided by square root of 2. So so now you can see that our stability criterion has actually become more restrictive. So square root of 2 is 1.4, so this one is smaller than 1. So now, just because we switch to 2 dimensions, our stability restriction on time step becomes becomes stronger. So our time step for 2-dimensional problem with the same speed. So this is kind of bizarre. So let's say that your flow is in this direction, only along the x direction. Then your stability criterion will be that time step, like based on mu, that is just in one direction smaller than 1. If all the flow in y direction is also less restrictive, but if you flow in 45 degrees angle, all of a sudden you should use smaller time step, even though the magnitude of wind is the same, say 5 meters per second, but now it's diagonally, and you have more restrictive scheme now. So this is a little bit strange. How you would explain it? Why so? So remember when we considered expansion, when we considered upstream bias scheme, we used our Taylor expansion and showed that this scheme is equivalent to advection plus some diffusion, which is implicit diffusion created by the scheme itself. And that those terms that diffusion coefficient for upstream biased scheme, this diffusion coefficient in x direction was something like u times delta x minus c delta t squared divided by 2. So that it also, if we write it in non-dimensional form, we have diffusion, so it's times delta t divided by delta x times delta x squared. So delta x squared, and here, so here is not like that, c squared, u squared, sorry. So we multiplied by delta t divided by delta x squared, and if you write it in a dimensionless form, we get something like 1/2 mu 1 minus mu. So from that we see that this diffusion, this implicit diffusion, is maximum, well, it's minimum when mu equal to 0, well, which means that there is no wind. Yeah, there is no diffusion then too. And then when wind is actually when mu equal to 1. In that case, it disappears too. And because it should be greater than 0, this is where explanation why mu should be smaller than 1. Because if it's bigger than 1, this diffusion coefficient is negative, and then it becomes unstable diffusion. So that's kind of physical explanation why we need this restriction on time step. But maximum, actually interesting, maximum diffusion occurs if you differentiate this, so dd mu, when it's maximum. It's mu minus 1 times mu. So it's equals to, you differentiate this one, sorry, 1 minus mu. So to find this maximum, we differentiate it. We have 1 minus mu and minus mu. So we have 1 minus mu, 2 mu equals to 0. This is, we'll find maximum of a function. So we have that mu equals to 1/2. This is what maximum effect of implicit diffusion. So when mu equals to 1/2, then it's maximum diffusion, implicit diffusion for upstream bias scheme. Okay, so what happens when we extend it in the 2 dimensions? First of all, you see this term, this guy contributes positively to diffusion. And it comes from Taylor expansion of this term, of space derivative. So it always creates this diffusion. This guy, which can actually create this negative diffusion, because you see it's subtracted here, comes actually from expanding this guy and replacing second derivative in time from that expansion using identity of wave equation. Remember that we have second derivative of phi over dt square. That's the term that we have there in the Taylor series, second term after a linear term. And then we found that it's equals to so it's d dt of d phi dt, and d phi dt is this guy. So in two dimensions though, it's and then from that we replace second derivative in time with second derivative in space, and in front of that, and here is also delta t over 2, and well, square. Yeah, square. And then we divide by delta t, so one will. So this is what diffusion, diffusive term produces, and so and then when expanded, we get the second derivative with this coefficient in front of it. In second derivative in space with this coefficient in front of it with minus sign because we move it to the right hand side. So, and that's what created all this instability. If mu is greater than 1, this pesky time term here. So, but now in two dimensions it's actually more complex than that. Let's substitute. So we have d dt, and here we substitute by this guy, so it's minus u d phi dx minus v d phi dy. So it's equals to minus u, and now we switch those derivatives. So we have d dx and again d phi dt, which we again replace minus u d phi dx minus v d phi dy, and minus v d dy minus u d phi dx minus v d phi dy. So now combining terms, we have the following, minus minus, so it becomes u squared, second derivative of 5 dx squared. This is exactly the term that we got before in the case of one dimension. And this is what produces this guy, diffusion with this guy. So, yeah. So, so it's this, I mean, this produces this term. So this is one, only in one dimension, it will be only this guy, that's it. But now we have dy too. So now we have the same term for y, similar term for y, second derivative of y, so it's diffusion in y now. But now we have actually a cross term. We have these guys, plus 2 uv this second derivative x dy. So this is the term. So those two would work like kind of okay, just direct expansion would produce a second term, and then if there was no this term, it would be the same. It's kind of very similar problem to before. But now we have actually additional guy that we only comes because of existence of y direction and wind in x or y directions. If they exist together, then this term is actually non-zero. So if you have like, even if you have second dimension, but if there is no wind in that direction, then this term is irrelevant. But as long as you have this wind in both directions, wind components in both directions, then you have this additional cross term. And this additional cross term is actually comes with negative sign here. And it acts like diffusion too, even though it's kind of weird diffusion cross. But this exactly this term that reduces stability of that scheme in two dimensions, of upstream bias scheme in two dimensions. So this is kind of physical explanation for that. And of course, in order to mitigate it, you need to have this kind of additional diffusion. And you see maximum at mu equal to 1/2. So the best actually to fight this guy is to produce maximum diffusion, which is mu equal to 1/2. So, and then total stability is 1/2 plus 1/2 equals to like 1. So that would be kind of a most optimal case. But so you see, this is kind of unorthodoxal. Well, it's not kind of straightforward. Stability in several directions can be kind of tricky. But so we established that for our upstream scheme, we have a stability criterion which is different than for two-dimensional upstream than for one-dimensional. So basically our velocity, if we use our CFL criterion based on the magnitude of velocity, then instead of 1 we should use 1 over divided by square root of 2. And in 3 dimensions it's actually similar. We can show that for 3 dimensions, but this time it's for 3 dimensions actually it's even more constrained. So for 1D you have that your mu should be smaller or equal than 1. For 2D you have that your mu should be smaller or equal than 1 over square root of 2. And for 3D you have that your mu based on magnitude of velocity. So mu equals to c delta t divided by 2 by delta x, or square root of u squared plus v squared plus w squared delta t divided by delta x. And so for 3D you will have 1 over square root of 3. So each time you get more and more restrictive time steps. So this is very unfortunate because you want a longer time step to compute smaller number of time steps to achieve your result. For example, because you're basically motivated by some you need say 1 day forecast. So 1 day is given, and then if you have like smaller, fewer time steps to achieve that 1 day simulation, the faster you actually would produce your simulation, the less computer resources you would use, and so that's always a good thing. And in this case, for 3D simulation, you require more and more time because you have smaller and smaller time step if you go from 1D to 3D. But it's not that straightforward for advection, because here we have this clear case of this mixed or cross derivatives that actually spoil our stability. But if you use other schemes, generally this is true for other schemes as well, but not always actually. You need to actually demonstrate that for each and every scheme. For some other schemes actually may not be the case. For multiple dimensions, it depends on a numerical algorithm you use. Actually, you need to test. Actually, when you say build a model, you make a test case. Say everything is in one direction. It's like along the x, width is in the x direction, and then you transport something with your scheme, and see if it's stable for your criterion. And then you change say direction to diagonal in all three diagonally, and see at which actually current number your model blows up. Sometimes, because model, it's not only, first of all, model is not only your advection algorithm. There are some other things that can dampen your solution and help with your stability, like subgrid scale, say diffusion scheme can actually help a little bit. And so you need to always test it. Don't just assume that theoretical limits are just correct, because otherwise you may have some stability problems with your model and not even realize that it's actually a stability problem. All you have to do is just reduce time step. But it is actually a good test. Like sometimes if you have some problem, like your model blows up, there are many things you need to look up. One of them may be try to reduce your stability criterion, make it more restrictive, say factor of 2, so you effectively run with time step which is half time step, and run it again and see if it's actually blows up, or you may discover that your solution has improved, which it should, because time step is smaller, but also because when you create constant instability, it generates excessive noise, even though it may not blow up, but it may generate excessive noise that actually can affect your solution. So, but generally, the rule of thumb, this is true. The more dimensions you use, the more constraint you should use. So if you have your scheme, you use your scheme in one dimension that is has some stability constraint, not necessarily one. It can be some A, I don't know, some mu naught. It can be 1/2, for example, for some schemes. Then this is basically use this rule of thumb. That if you apply this in your three-dimensional model, you need to reduce it further. But you need to check it. Sometimes some schemes don't work like that. Now for diffusion, if we use simple Euler time diffusion, so we have diffusion equation and like that. So we have, say, nu and x second derivative x squared plus nu y second derivative and y nu z second derivative in z. So let's say we now expand. We may expand directly using, like, say, ijk indices here, n plus 1 minus phi ijk divided by delta t. We use just nu x, and here we have like I plus 1 jk minus 2 phi I jk plus phi I minus 1 jk divided by delta x squared plus, and similar term for y direction, similar term for k direction. Then the question is, what stability of the scheme? For one dimensions, we established the other day that stability criterion is for 1D, that nu times delta t divided by delta x squared should be smaller or equal than 1/2. So this we established for one-dimensional case. So how about this two-dimensional or three-dimensional case? Well, it's actually the similar thing. They should be, they kind of added these mu's. So basically what you have is nu x divided by delta x squared plus nu y divided by y squared plus nu z delta z squared times delta t should be smaller or equal than 1/2. So now we have, if for example delta x equals to delta y equals to delta z, simplest case, and nu x equals to nu y equals nu z equals to nu, then it's easy to see that actually we have now condition which is like 3 nu delta t divided by delta x squared smaller than 1/2. So we have actually now, if we divide by 3, we have 1/6 for 3 dimensions. So in 3D we have nu delta t divided by delta x squared smaller or equal than 1/6. It's much less stable. So our delta t should be in 3 dimensions for diffusion problem should be something like 3 times smaller than similar diffusion problem in 1 dimensions. So that's very important to remember when you code your model. So is there any way to avoid all these restrictions? Because this is not very good when you need to divide time step like that. So you see that diffusion is even more restrictive than advection in this case, because we had a square root of 3 in case of advection, and here we have just 3. that we divide with. Another example of problems that you may get when you moved into multiple dimensions is this kind of classical example of Lax-Wendroff scheme instability in 3 dimensions or in 2 and higher dimensions. Let me remind you what Lax-Wendroff scheme is. So it's Lax-Wendroff scheme. It's a scheme that uses this artificial added diffusion terms to fight this implicit diffusion with negative diffusion that from this time derivative that we considered before. But in this case, in the case when you use central in space scheme, not upstream bias. So Lax-Wendroff in 1D looks like phi km, okay, not km. So phi k n plus 1 minus phi k n divided by delta t equals to this diffusion, advection, k plus 1 n minus phi k minus 1 n divided by 2 delta x. And remember, if we try to leave it like this, remember on one of our previous lectures, it actually can be shown that the scheme is absolutely unstable. It will blow up no matter what because of this central scheme. And the reason is because you have this diffusion that arises from this time derivative approximation. If you expand, as I showed before, the second order derivative in time translates into second order derivative in space with negative diffusion coefficient. So in order to compensate, we need to add this diffusion coefficient explicitly to cancel it out. So we have scheme like this, c squared delta t divided by 2, and here we have just diffusion. So this is Lax-Wendroff scheme, or Crowley scheme, one-dimensional one. So if you now expand this scheme to 2D, so for 2D you just add this another term. So instead of C it's going to be so you will get like let's write it as U. So it's U square. So then you just add, for 2D you add V, you make it M, 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 M. And here you have just K, N plus 1, N minus phi, K, N minus 1, N divided by 2 delta Y. And then you just doing the same similar thing. You now diffusion in Y direction. So you would think that you're done. So you just expanded it to 2 dimensions like that directly, and then you'll done. And maybe you reduce your stability by a square root of 2 stability criterion. But the problem is this scheme becomes absolutely unstable for 2 dimensions or 3 dimensions if you expand it to 3 dimensions. Regardless, it's absolutely unstable for any mu. So it was stable for 1 dimension and it's absolutely unstable for 2 dimensions. And the reason is that cross term that we kind of compensated in upstream bias scheme by providing this very strong diffusion. But here, because we use center differences, there is no this implicit diffusion anymore because of this. Those terms cancel out. So which is only left is a diffusion due to time derivative. And those two things compensate for second derivative in x and second derivative in y, but those terms don't compensate for this cross derivative. So in order to make this scheme stable, we actually need to edit this cross terms. So we need to add the following. We need to add term u times v, and then it's going to be 2 well, I don't remember quite coefficient here. Shouldn't be 1/8. So we need to use okay, so I think it just like that, yes. UV delta t, and then here we need to make approximations for the derivatives, this cross, so how you approximate mixed derivative. So you use this pattern. This is I, M, K, M. So you use now, so this is becomes phi K plus 1 M plus 1 minus phi K minus 1 M plus 1. This is d dx and divided by delta 2 delta x, and minus, and now you make a derivative in y, so it minus f k plus 1 m minus 1 minus phi k minus 1 m minus 1 divided by 2 delta y, and you divide it by delta no, this one is delta x, this is delta y. So see how, this is how you approximate this derivative and km. So you need to add this guy in here, and because it's there was like 2 UV, and it's symmetrical, so you can actually check that this expression, if you write it d dx dy, is the same as d dy dx. It's symmetrical. So you will add, and so you need to add cross term diffusion, and then it becomes stable for stability. So it's a little modification. You need to turn like that, and then it will fix it, and then it will be stable for 2 dimensions. And now and it will be stable for mu smaller than 1 as before, for 1 dimensions. So in 2 dimensions it will be as well stable, because you completely cancel this term, unlike upstream by steam, you don't explicitly cancel it. So you cancel this, this scheme becomes stable with this term. Of course, instead you can completely avoid, for this case you can add this additional term, but for other cases you may completely avoid this additional restriction on stability by using so-called directional splitting. So what's directional splitting? Well, like name implies, you just apply your scheme first in one direction, then in the other direction separately. So directional splitting so you have you do the following. For example, for upstream bias scheme, you use the following, that you have this provisional minus km minus phi km n divided by delta t equals to minus u phi n k plus km minus phi n k minus 1 m divided by delta x. So this is your upstream bias scheme in x direction, and then you use solution from that to drive solution in y direction. And this kind of, it becomes n plus 1 minus phi n divided by delta t equals to minus v phi k m star minus phi k m minus 1 star divided by delta y. So you see, you just you have two steps. First you apply upstream bias scheme in x direction. After you find solution, you use that solution as a initial conditions for solution in another direction, in a different direction. And for each of those steps, of course, mu x should be smaller than 1 and mu y is smaller than 1. So you see, it's much less restrictive. So you can use a longer time steps. Actually, these two schemes can be combined into one scheme. If you just substitute, get rid of this star, you substitute this star into this, and you write this two-step scheme as one-step scheme. And it is written like the following, that phi k m n plus 1 equals to 1 minus mu x 1 minus mu y phi k m n plus mu y phi k m minus 1 plus mu x 1 minus mu y phi k minus 1 m plus mu y phi k minus 1 m minus 1. And this scheme is called corner transport. Corner transport. Not upstream biased. Why corner? Because you see, if you look, unlike our direct expansion of our one-dimensional upstream bias scheme into two-dimensional case, when you had only, we have only, so this is k, this is m, so our pattern looked like this. So we used these 2 points in x for, these 2 points for x direction and these 2 points y direction. Here we actually have points k, m as before, k minus 1 m, so those guys. Or actually, no, upstream bias, so it's, sorry, yeah, so we use this, so it's minus 1, minus 1. This is m, k, m, so it's k minus 1, m minus 1, k, m. We used only 3 points, now we have actually additional one, this point. And that's actually why this scheme becomes less restrictive, because basically if you analyze it, we got rid of mixed derivative term by doing so. And this is kind of why we get this guides from our mixed derivative. And so this is additional point what we actually introduced, and introducing this point kind of fixes the stability of the scheme. And it's called corner transport. I don't know, so this is this corner, I don't know, some special corner here. So it's not quite upstream bias scheme, because if you write upstream bias scheme, it's written slightly differently. This one is, it has the same first order in space and time truncation, but it's stable for much less restrictive in case of stability. So you see, directional splitting can be one of the solutions to the stability problem in multiple dimensions, but it comes also with some disadvantages. I mean, this directional splitting. Of course, it would be great if it was like worked all the time. The problem is that when you directly split, you kind of lose some information about the three-dimensional structure of the flow. In this case, U and V are constants, and because we consider linear stability and everything is linear, so it doesn't really matter. But if you use actual flow, can be very non-constant, like you have, like I don't know, this is your actual flow, and you're transporting some phi, some scalar, let's say, using this very non-uniform flow, and so there is so-called non-divergence conditions. Flow usually, like if it's like say water, not compressible, there is continuity of mass that simply says that divergence of velocity equals to 0. And it's three-dimensional property. It doesn't come like divergence in x should be 0 and divergence in y. It's divergence in x and in y combined creates 0. So you can have convergence in x, divergence in y, together it's 0. In this approach, it doesn't know about this. These equations don't know about this. And actually, if you apply consequently some algorithm that, let's say that you have this flow like this, and you have phi which is completely constant, say temperature. It's constant everywhere, it's 300 Kelvin. But your flow is very, very chaotic. In physics, in reality, it wouldn't change this 300 Kelvin. It will be still 300 Kelvin everywhere. But because you have here, if you apply this algorithm and use so-called conservative, the scheme in flux form, we're going to talk about that later. If you apply this algorithm in flux form, it actually doesn't know about this convergence property anymore. And it will generate you noise in temperature. So it will create 300 plus minus some value fluctuations of temperature just because you split the scheme. So sometimes people forget about that and design this very nice behaving, nice, beautiful one-dimensional transport algorithm, and then just extend it to 3 dimensions, show that it works great in 1 dimension, and then apply it to 3 dimensions. And all sorts of problems arise. All this noise and others, so they start developing limiters, some artificial fixers that kind of prevent this. It's because you move to 3 dimensions and all of a sudden your beautiful one-dimensional transport algorithm is not that good anymore. So just keep that in mind. It's better that if you design some 3-dimensional transport algorithm, make it 3-dimensional from the beginning. That would make your life much easier. And we're going to talk about some of those in the future lectures when we talk about transport algorithm for scalars. Okay, I think that's enough for today. See you later.